is it fairly light?
Welcome everybody. Thank you for coming on this wet afternoon. I hope it hasn't put too much of a dampener on your spirits. I'm sure we'll be invigorated though by what Nick has to tell us about this afternoon. So it's a great pleasure to welcome Nick Ormrod to our Thursday seminar. Nick's the DPhil student in the quantum group in computer science, working with our close friend and colleague John Barrett. And he's going to be giving us insight how to go beyond the big three. Over to you, Nick.
Thanks. Okay, so there's an approach, there's an attitude towards interpreting quantum theory that's not so uncommon that goes something like this. The idea is that if you're somebody who wants to get a precise and a realistic understanding of what the quantum formalism is saying, then unfortunately you've not really got any more than about three big options. You could add variables to the quantum state, you could modify its dynamics, or you could do neither of those two things, as long as you learn to live with the multiplicity of worlds that appears to follow. You can do something like Bohm theory, something like GRW, something like Everett, and if you don't want to do all of those, if you don't want to do any of those things, then that's fine. But the assumption here is that that means that you're not just giving up on a particular set of theoretical proposals. The assumption here is that that means you have to give up on the very idea of providing any precise realistic understanding of the formalism whatsoever. But today I want to argue that at best, that's a very premature judgment. I think it's likely that there are viable, precise realist options beyond the big three. And in fact, I'd go so far as to suggest that probably our only viable options lie there. And I might be wrong, but in any case, what I do want to argue is that we're not yet in a position to know that we can't go beyond the big three. And as such, we should be devoting considerable energy and resources in that direction. And the argument that I'm going to make for this is not going to be abstract. It's going to be concrete. I'm going to show you a new interpretation of quantum theory that I've been developing recently together with John Barrett. And it's not that I want to say that this interpretation is flawless, and it's not even that I want to say that it's completely empirically adequate in its current form. But what I do want to say of it is that it does provide you with a precise and realistic description of at least some possible world. And moreover, it's a possible world in which the statistics that you expect from standard finite dimensional quantum theory are upheld. And so the main purpose of this talk, really, or my main task for this talk, is to explain to you how this interpretation works. And it's probably a good idea to start with the big picture. And there is a big idea which kind of distinguishes the interpretation I'm going to lay out from at least most incarnations of the big three. When you look at the big three, or at least most versions of the big three, something that's clear that they've got in common is that they all seem to subscribe to this particular paradigm for doing physics. It's been highly influential throughout the history of physics. I'm talking about the paradigm of kinematics and dynamics, right? On this way of doing physics, you describe reality using some kind of kinematical object, usually called a state. And then the primary role of the dynamics is to constrain or to transform that state. So it might be that your theory works by you specifying some kind of initial condition a priori, and then using the dynamical rule in order to transform that initial condition into a subsequent condition. But more generally, the role of dynamics is to transform a partial description of the state of the world into a more complete one, at least according to some probability distribution. But our interpretation works a little bit differently. On our interpretation, there isn't an initial condition. Or at least there's no kinematical initial condition. The closest thing that we've got to an initial condition is a dynamical structure. That's the only thing that we lay down a priori. And once we do that, we see kinematics, we see the space of states emerging out of that dynamics in a way that is precisely mathematically characterizable and calculable. That's the big idea. And now what I want to do is to convey that in much more thorough detail. And in order to do that, I've divided the main talk. I've divided the main part of the talk into these two different parts. So first of all, I'm going to talk about the ingredients that go into the interpretation. So that is going to include some important definitions of some key concepts, and also some mathematical theorems without which the interpretation simply wouldn't make any sense. Having said that, everything in the ingredients section is just a comment on how the structure of standard finite dimensional quantum theory works. So nothing that I say in part 1 should really depend on any interpretational commitments. But part 2 is where I am going to make some interpretational commitments. Okay, so the ingredients that go into the interpretation can be summed up with this sentence. Causal decoherence singles out projectors which admit probabilities. And I'm going to be unpacking this sentence over the next half hour or so. So first of all, we're starting with this idea of causal decoherence. Now, I expect that most of you are familiar with the broad idea of decoherence. Roughly speaking, the idea of decoherence is it's the suppression of quantum interference effects. But of course, there are different ways that you can try to pin down that idea technically. So one definition that you could give of decoherence is you could say that decoherence is just what happens when my quantum state, when my density matrix, when its off-diagonal terms vanish or nearly vanish. And that would be a purely kinematical definition of decoherence because it just supervenes on the density matrix. But on the other hand, what is arguably a slightly more sophisticated definition of decoherence would involve talking about the evolution of that density matrix through time. You could use something like the consistent histories formalism, and you could say decoherence is what happens when my different histories for how the quantum state could evolve, their interference vanishes or nearly vanishes. And then that would be a partly dynamical definition of decoherence, but it's still partly kinematical, right? Because you're still talking about the state. You have to sort of assume a priori that you began with this particular quantum state. The way that I'm going to treat decoherence now is different. It's purely dynamical and is not kinematical whatsoever. It will not require the specification of any quantum state. And more precisely than being purely dynamical, it's purely causal. It only refers to the causal structure of the dynamics. Okay, so let's see what that means. So throughout this talk, I'm just going to be concerned with finite dimensional quantum theory. That is the only thing that our interpretation applies to so far. So I want you to imagine that you've got some finite dimensional quantum system. That's a system that can be represented with a finite dimensional Hilbert space. And a projective decomposition on that system is a set of projectors onto the Hilbert space of the system, which are mutually orthogonal and which are complete in the sense that they sum to the identity operator. So the idea is that the Hilbert space is a direct sum of a bunch of orthogonal subspaces, and each projector in a projective decomposition projects onto one of those subspaces. Now, on this slide, and also on throughout the next several slides, I want you to assume that you've just been given some particular unitary transformation, right? That's our setting. You've been given a finite dimensional unitary transformation whose input subsystems are A and B, and whose outputs are C and D. And you've also just been given a particular projective decomposition on A and one on D. Now, it's useful to define the Heisenberg representations of these projectors. So the Heisenberg representation of the A projectors, that's just going to involve tensor producting the projectors with the identity operator on B's Hilbert space. That means that now your projectors formally live on the whole input space of the unitary transformation. And we sort of do an analogous thing with the D projectors, except we're going to end up rolling them backwards through the unitary so that they also act on the input space of the unitary rather than the output. That's because we want to consider our different projectors as living on the same formal space. And in particular, that's going to help us with the following definition. So the first definition that I'm going to give you is a definition of a particular type of causal relation that can hold between our two projective decompositions. The projective decomposition on A exerts an interference influence on the one on D if there exists an I and a J such that the projectors do not commute, the corresponding projectors do not commute in the Heisenberg picture. So you see, the idea of an interference influence is a simple one. Interference influences are simply non-commutation relations in the Heisenberg picture. It's such a simple idea that it kind of begs the question of why I'm glorifying it with this fancy terminology of interference influences, right? Why am I talking about it as being some kind of causal influence when really it's just a non-commutation relation? Well, one justification for that comes through this first theorem. It says the decomposition on A exerts an interference influence on the one on D, if and only if an agent who shifts the relative phases between the A projectors via a unitary transformation of this form could in principle signal to an agent who does the projector valued measurement defined by the projectors on D. You see, the intuition here is that having an interference influence means that the D projectors are affected or influenced by the interference between the A projectors. So that's why it kind of makes sense to call it an interference influence. Now, having just made that argument, I should immediately clear up a possible confusion that could follow from it. It's not that I'm trying to say, by quoting Theorem 1, that I think that causation is essentially wrapped up in the concepts of agents and signaling and other operational concepts like that. To the contrary, I want to define causation as this purely dynamical property, and therefore it's as an agent-independent one. But nevertheless, when there is an in-principle possibility of signaling between agents, it makes sense to say that there must be a causal influence which those agents are exploiting. That's all I mean by this argument.
Just a clarificatory question. Here, when you say shifts the relative phase between the PIA, you mean for the same A, for that unitary to which you define the A, and it's between the different PIs of your original composition, right? Projector.
Yeah, that sounds right. Yeah, so the idea is, remember, you've got this unitary transformation from AB to CD. The setting here is that there's an agent who acts on A before that unitary is implemented. That agent is allowed to do whatever transformation they like as long as it's of this form. And we're asking about whether that agent can signal to an agent who does this projector valued measurement after the unitary is implemented. Okay. So we defined interference influences as non-commutation relations in the Heisenberg picture, and we see that they correspond to this idea that the D projectors are sensitive to the relative phases between the A projectors. That definition of interference influences is now going to allow us to define decoherence in a causal way. Decoherence now, for me, is going to become an absence of interference influence. So definition 2, the projective decomposition on A is decoherent relative to D if the decomposition on A does not exert an interference influence on any projective decomposition on D. And bearing in mind Theorem 1, Theorem 2 is not very difficult to prove. It says that the projective decomposition on A is decoherent relative to D if and only if an agent who shifts the relative phases between the A projectors via the same unitary we saw before could never, in principle, signal to an agent who can perform any measurement they like now on D. So the intuition that leads me to call this thing a decoherence relation is that the entire system now of D doesn't encode any information whatsoever about the relative phases between this particular projective decomposition on A. Now, at risk of repeating myself, throughout these last 3 slides, I've been asking you to assume you've been given a particular unitary transformation, but I never at any point had to mention a particular quantum state. Right? So unlike some other definitions of decoherence that you might be familiar with, the question of whether or not a given projective decomposition is decoherent is settled entirely by the unitary transformation. And more precisely, it's settled entirely by the interference influences through that unitary transformation. So we have our notion of causal decoherence.
Can I just ask a question?
Yeah.
When you say any agent who can perform any measurement on D,
Yeah.
how do you define the notion of measurement without referring to states?
Yeah, that's a very good question. So right now, I am just trying to lay out the ingredients for the interpretation. And in doing so, I'm just kind of telling you things about the structure of standard quantum theory. So my definition of signaling actually is going to involve states, right? It's going to involve saying that A and B started off in some particular state, and then Alice can perform some transformation, and then Dave at the end is doing some measurement. Nevertheless, I still don't have to refer to any particular state because it's going to involve quantifying over all possible states on A and B. So it remains the case that I don't have to specify any quantum state in order to give this definition. Okay, good. So remember, our sentence was that causal decoherence singles out projectors which admit probabilities. So now we're going to see about how these projectors are singled out. I think the easiest thing to do is to start with a couple of examples. And we're going to begin with an extremely simple example, which is just a C0 transformation. This is a unitary transformation whose inputs are 2 qubits to 2-dimensional quantum systems, and whose outputs are another 2 qubits. And so in this definition, the kets with the zeros and ones inside them, they refer to this orthonormal basis for the Hilbert space. I might sometimes call that basis a computational basis or the Z basis, but you don't need to read too much into that terminology. And roughly speaking, the idea of this unitary transformation is that the transformation that maps B into D is going to get controlled by A in some sense. That's kind of the intuition. Now, there's a fact about this unitary transformation, which is that the only projective decompositions on A that are decoherent relative to D are those two. The projectors onto the computational basis and the trivial projective decomposition, which only contains the identity operator. So at least in this case, it seems clear that there is a unique projective decomposition that's singled out by causal decoherence, because there's only one non-trivial one. But the thing is, this is a highly simple and contrived example, right? So that doesn't establish that we're always going to be able to single out a preferred projective decomposition. So let's now see a very slightly more complicated example. As you can see, it's a bit like the C0 transformation, only now A and C have been promoted to 3-dimensional rather than 2-dimensional systems. And now we've got this rank 2 projector, which is going to lead to this X transformation mapping B into D. Now, this is only slightly more complicated than example 1, and yet, now, far from having a unique non-trivial projective decomposition that's decoherent relative to D, now we've got an infinite set, an uncountably infinite set of projective decompositions that are decoherent. So if there is some kind of singling out going on, it's not singling it out in the same way. Nevertheless, I want to argue that even in this example, there is a unique projective decomposition which in some sense is marked out as special by the idea of causal decoherence. And I'm not going to tell you exactly what it is yet, but I am giving you a hint, which is that it's one of these 4 projective decompositions. Where, by the way, this notation, so the 1 plus 2 state, that means an even superposition of the 1 state and the 2 state. Now, does anybody want to hazard a guess as to which one I'm going to say is preferred?
D1.
Say again?
D1.
No, not D1. So the reason I don't want to say that D1 is preferred is that, yes, D1 is decoherent relative to D, but so is D2. And D1 and D2 are kind of similar, at least with respect to that unitary transformation. One way of understanding how they're similar is to note that they differ by a unitary transformation. I can sort of do a unitary rotation that transforms D1 into D2. And actually, not only D1 and D2, but there's this uncountably infinite spectrum of projective decompositions which all differ by this unitary transformation, and all of them are equally decoherent relative to D. And so actually it's not really clear that there could be any principle that allows you to pluck out one member of that infinite spectrum and to say that this one is preferred. So actually I don't want to say that D1 is preferred, and by the same argument I don't want to say that D2 is preferred. That leaves us with D3 and D4. And the thing about D3 and D4 is that neither of them are vulnerable to the same kind of argument that I just used to rule out D1 and D2. And out of them, one of them is more fine-grained, and I'm going to suggest we want to take that. Okay. But then the question is this bit of reasoning that I've given you a kind of ad hoc idea that can only be applied to this specific example? Or can we actually generalize it into a definition of decoherence that will always succeed in singling out a unique projective decomposition? And it won't surprise you to hear me say that the latter is true. We can turn this sort of intuition into a general definition of preference. So here's the definition. A projective decomposition on A is preferred by D if it is the most fine-grained projective decomposition on A that satisfies 2 properties. It's decoherent relative to D, and it commutes with all other projective decompositions on A that are decoherent relative to D, right? So if we go back to our previous example, this is decoherent relative to D. D1, that is decoherent relative to D, and it's as fine-grained as you can get. However, it doesn't commute with all of the other projective decompositions that are decoherent relative to D. So that's why it gets ruled out. Now, admittedly, definition 3, I am claiming that it's sort of, if you think about it for long enough, I am claiming that it is the conceptually well-motivated definition. However, it's a little bit wordy. But that's why it's kind of good to show you this theorem 3 that I'm going to explain to you in a second. So first of all, we need to define some operator algebraic concepts. So curly A is going to be the algebra or the set of all of the operators that act on A and A alone. Curly D is the set of operators that act on D and D alone, only we're in the Heisenberg picture. So again, we're going to roll back these operators into the input space of the unitary transformation. I want to define the commutant of X, comm X, as the set of operators that commute with all of the operators in the set X, and the center of X is the intersection of X with its own commutant. Now, with those definitions in place, we can state theorem 3. Theorem 3 says that the projective decomposition on A is preferred in the sense of definition 3, if and only if it satisfies that equation. Okay? So essentially, to give an intuition for what this equation is saying, on the right-hand side, first of all, I'm taking the intersection of A with comm D, so that means I'm asking for the set of operators on A, which have the property that they commute with all of the operators on D. And then I'm asking for the center of that algebra of operators. Now, it's a general result in the theory of operator algebras, at least in the theory in the finite dimensional theory, that the center of an operator algebra is always, it can always be written as the span, that is the linear combinations that you get from some unique projective decomposition. And theorem 3 says that that projective decomposition is precisely the preferred one. Now, if you're not familiar with some of these operator algebraic ideas, then what I said might seem a little bit opaque, but even if that's the case, that's fine, because actually the finer details of theorem 3 don't concern us too much. I only mention it because I want to make 2 points with it. So the first point that I want to make by stating theorem 3 is that although this is a bit wordy when I state it with words, it's quite natural on a mathematical level. And the second point that I want to make is uniqueness. So a corollary of theorem 3 is that there is exactly one projective decomposition on A that is preferred by D. And this is for a general finite dimensional unitary transformation. And indeed, this notion of preference is going to single out the projective decompositions, which I argued were preferred in the previous 2 examples. Okay. So that's progress. We've got this general notion of how causal decoherence can single out a unique projective decomposition on an input subsystem to a unitary relative to any given output. However, that's not us done for the bit about decoherence singling out projectors, because the problem is that there's not a lot of interesting stuff that you can model with just a single unitary transformation. In general, your dynamical situation might be a lot more complicated than anything that can be described nicely with just one unitary transformation. And more generally, you might want to think about dynamical structures that can be represented with circuits. Right? Circuits are what you get by plugging together a bunch of these individual unitary transformations in order to form a network. Now, I want to define, just as a bit of terminology, a bubble as meaning a subset of the systems, i.e. the wires in some unitary circuit. And then I want to ask a more general question about how we can single out projectors using causal decoherence. The question is, can we now single out a set of preferred projective decompositions relative to an arbitrary bubble in an arbitrary unitary circuit? And the answer is yes, we can. But here's how we do it. First of all, I need to pick the bubble that I want to derive preferred projective decompositions for. So here I've chosen A1, A2, and A3. Nothing special about that choice, it's just an example. And the first thing that I do is I make cuts in the wires, all of the wires that are inside of my bubble. Once I've made these cuts now, I've got, for every system in the bubble, I've got a wire that goes into the cut, which I'm calling A something in, and a wire which goes out of the cut, which I'm calling A something out. And then the next thing that I do is I take those wires, and I take the wires that go into the cut, and I pull them up to the top of the page, and I take the wires that go out of the cut, and I pull them down to the bottom of the page. So that's what we've got on the top right. And it's a bit confusing because now the wires that came out of the cut are going into the circuit, and the wires that were going into the cut are coming out of the circuit. But there you go. Now, this circuit on the top right is another unitary circuit, right? It's made up of unitary transformations, and therefore, the whole thing can be understood as a single unitary transformation, which is good, because we already have a definition of preference that can apply to a single shot unitary transformation. And moreover, this unitary transformation has a nice interpretation, which is that essentially, it's the unitary transformation that allows us to represent the direct influences between the different systems in the bubble, but without representing any of the indirect influences that are transmitted via other systems in the bubble. So it's a unitary transformation that defines the direct causal interactions within the bubble. So I'm going to use that. Yeah?
The preference was defined for 2 inputs and 2 outputs?
Ah, yes. But in general, if I've got n inputs and m outputs, then I can take the input and the output that I'm interested in, and then I can just group all of the remaining inputs into one system, and I can group all of the remaining outputs into one system, and then we go back to the kind of situation that preference was defined for. And the fact of doing that grouping isn't going to change anything about what's preferred. But yeah, good question. So I've got my unitary transformation that represents the direct causal interactions within the bubble. And now I'm going to apply that definition that I've already got in order to identify preferred projective decompositions. So I'm going to start with A1 out. This is a wire that was going out of the first cut in the bubble, but now is going into the unitary transformation. And what I'm going to do, roughly speaking, is I'm going to ask for the unique decomposition that is preferred by the tensor product of all of the other systems in the bubble, right? The tensor product of these 3 systems in particular. Similarly, I'm going to ask for the decomposition on A2 out that is preferred by all the systems in the bubble, and I'm going to do the same thing for A3 out. And at that point, for my bubble of 3 systems, I've singled out 3 projective decompositions, 1 for each system. And you might think that we should stop there, but we shouldn't. And the reason why we shouldn't is because all of the relevant concepts here are sort of symmetric in time. In particular, interference influences are symmetric in time. It doesn't matter what direction of time we conceive of. And if we just left it there, then we would be introducing a time asymmetry by hand, right? Because, if we were considering time going in the other direction, then we would have derived preferred decompositions for these guys. And so because I want to avoid a time asymmetry, I'm also going to do the same thing for these systems. And I'm going to sort of ask, for A1 in, for example, I'm going to ask what is the unique decomposition that is singled out by causal decoherence, sort of in the other direction of time. Good, so now for my bubble of 3 systems, I now have 6 projective decompositions. For every individual system, I have 2 projective decompositions, and each projective decomposition of the 2 is associated with a different direction of time. And in particular, the projective decomposition on the systems that I've labeled in, they're sort of derived from the interactions of the system with its past. Whereas the projective decompositions on the wires that went out of the cut, they are derived from the interactions of the system with its future. Okay. And more generally, what I have here is I have a means of, given a bubble of n systems, I can get 2 n projective decompositions, 2 for each system, one associated with one direction of time, the other associated with the other direction of time. Good. So I've done what I wanted to do, which is single out a set of projective decompositions relative to an arbitrary bubble of an arbitrary unitary circuit. And it turns out to be worthwhile at this point to ask a particular question. Having derived all of my preferred decompositions, I can now go back to the original unitary circuit that I started with, and I can redecorate that circuit using the derived decomposition. So that's what I've done with this picture. And then I can ask a question, which is, in general, what kind of interference influences can I have between the different projective decompositions in the bubble? And it turns out that there is a non-trivial thing we can say about that. The red arrows in this picture represent the only possible interference influences we can have. So the presence of a red arrow doesn't mean we necessarily will have an interference influence, but the absence of a red arrow means that we cannot have an interference influence, right? This picture represents the constraints on the interference influences. Now, you can notice the pattern, hopefully. I can only get projective decompositions from the ins to the outs. Sorry, I can only get interference influences from the ins to the outs. If we remember the interpretation of those decompositions, then that means I can only have interference influences from the decompositions that were derived from the interactions with the past going towards the decompositions that were derived from the interactions with the future. And that has an important corollary, which is that you can't get any chains formed by these interference influences. Right? You can't get multiple, you can get individual arrows, but you can't get multiple arrows in a row forming this directed path. And that is the causal fact that is behind the final part of our sentence. Causal decoherence singles out projectors which admit probabilities. Remember, the definition of an interference influence was a non-commutation relation in the Heisenberg picture. And so you can probably believe what this theorem 4 says. It says, given the set of projective decompositions that are singled out by causal decoherence relative to a bubble, the following expression defines a probability distribution. So in this expression, what I'm doing is I'm just lining up all of the projectors in the Heisenberg picture in the order that they appeared in the circuit in a picture like this. I'm lining them up. I am tracing them and then dividing through by the dimension of the Hilbert space. Now, in general, an expression like this in quantum theory doesn't return a probability distribution. Because in general, you can get negative numbers or you can even get complex numbers. But what the theorem is saying is that in this case, when you single out the projectors by causal decoherence, you do get a probability distribution. And I'm not actually going to go through the proof with you right now, but you can probably sort of get the kind of idea of it. There are no chains of interference influences, which means there are no chained non-commutation relations. And where things go wrong in quantum theory, or at least where things get non-classical in quantum theory, is where you've got non-commutation relations. And so it's kind of interesting that we're allowed to have a bit of non-commutation, but somehow there's this sort of constraint that limits the amount of non-commutation that we can have, and it limits it enough such that we always get a valid probability distribution. Good. So, part 1 was saying that causal decoherence singles out projectors which admit probabilities. Causal decoherence, remember, is defined entirely in terms of these causal influences called interference influences, and they don't rely on the specification of any particular quantum state. Singles out projectors, so that's not quite true. More precisely, it's sets of projective decompositions that get singled out by causal decoherence. And more precisely, we get 2 n projective decompositions relative to a bubble of n systems. And there's this particular fact about the interference influences you can have within a bubble, namely that they don't form chains, which means that what we get is not just any set of 2n projective decompositions, we get one of those rare sets of projective decompositions that that give us valid probabilities via a linear trace rule like this. Okay. So we're doing kind of all right for time. Are there any questions at this point? Yeah.
So these are probabilities of what or over what?
Oh yeah, good point. So I was trying to make this first part entirely independent of interpretation. So when I say which admit probabilities, I mean a purely mathematical thing.
Yeah, but still, what's the set that contains E1s and ENs?
Okay, so you've got these projective decompositions. There's a certain number of decompositions in the set. E1 is just a sort of classical variable that labels which projector in my projective decomposition I've got.
Oh, okay.
Yeah, yeah. So I might have, if I've got a set of 3 projectors in a projective decomposition, I might call them P0, P1, P2, and then E is the variable that can take the values 0, 1, and 2. Good. All right. So having laid out all of these ingredients, the actual interpretation is not so difficult to state. I can give you the main idea in one sentence. It's relative to each bubble, one history is realized. But let me now try to lay that out in greater detail. So here are some axioms. The dynamics in our theory are given by a finite dimensional unitary circuit C. The fact that C takes place is a primitive and observer-independent fact about reality. So all I really mean to say by that is that the only kind of initial condition we've got in our theory is a dynamical initial condition, and concretely it's a unitary circuit. Then we define a bubble as a subset of the systems, i.e. the wires in the circuit. A bubble V of n systems is associated with the preferred set of 2 n projective decompositions. That's the set that gets singled out by causal decoherence in the way that I explained to you using that flow chart. Now, relative to each bubble, we posit that 2 n events take place. So each event is mathematically represented as the selection of a unique projector from an element, i.e. from a particular decomposition within our preferred set of decompositions. Right? So now we're making an interpretive claim here. We're saying we've got these projective decompositions, and for each decomposition in our bubble, we're saying that one projector gets kind of chosen, and that's what we mean by an event. And they don't get chosen deterministically, they get chosen probabilistically. And the probability for those events is given by this linear trace rule that you've already seen. Now, to connect it explicitly to the sentence from the previous slide, a history is just a list of all of the events that happen in a bubble. So it's all of the 2n events. So you can interpret this probability as being the probability of either 2n events, or equivalently, as the probability of a particular history to take place. So again, the claim is that relative to each bubble, one history is realized. And that's all there is to the interpretation. But now I'm going to try to get you more of a feel for it by actually applying it to some examples. So here is what I believe is the most simple but still not completely trivial example I can give. It's a simple circuit. It just consists of a C-naught transformation. We have 4 systems. That means that there are 2 to the power of 4 bubbles, right? Because that's the number of subsets there are of a set of 4 things. So there's 16 bubbles. Already in this fairly simple circuit, we're saying there are 16 different bubbles, and technically, we're claiming that one history gets realized relative to every one of those 16 bubbles. Although it is also worth noting that in most bubbles, not much happens. In fact, you could argue that nothing happens. So if I take a bubble that only includes the system A, I can do that, and then I can derive the 2 preferred projective decompositions that I'm going to get from that bubble. But if my bubble just includes A, then those decompositions are going to be trivial in both cases. Both decompositions are going to be the ones that only contain the identity operator. And that means that there's only one, that means that each projective decomposition only gives rise to a kind of trivial event because it has to be the same every time. And that means that there's only one possible history that can take place. And I don't know about you, but it seems to me that if only one thing can happen, it's kind of like nothing happens. So that's why I say that not much happens. And actually, the same goes for most of these 16 bubbles. In most of them, you just don't really get anything happening. But there are some bubbles in which some things do happen. So here's a relatively interesting bubble in the C-naught. It's the bubble that contains A and D. We have 2 systems in this bubble, which means 4 preferred decompositions, but 2 of them are trivial, which means that we only get 2 non-trivial events getting defined by our projective decompositions. And I've called those events ZA and XD. I'm going to be using this terminology, so it's worth explaining it. The reason I'm calling this ZA is because it's a selection of a unique projector onto the Z basis. And the reason why I'm labeling this event XD is because it's a selection of a unique projector onto the X basis, which is made up of sort of superpositions of the Z basis states. So we only have 2 non-trivial events. We only have 4 possible histories. And guess what? Each of them is attributed 1/4. And so we've got a uniform probability distribution. We have no correlations between our different event variables. So it's relatively interesting in the sense that we do have some non-trivial decompositions, but it's also very boring in the sense that there's no correlations in this bubble. But we do get more interesting bubbles in more elaborate circuits. So here's an interesting example. This is a picture where all of the systems are two-dimensional. I've got a couple of C0 gates, and I've got some arbitrary unitary transformation U. Now, this picture, you'll see that I've opened up certain systems. That means I'm drawing your attention to a particular bubble. I'm drawing your attention to a bubble that contains 4 systems, which means that technically we've got 8 decompositions, but in this case, actually, only 4 of them are non-trivial. We find something interesting when we look at the statistics. So remember, I've got this probability rule that allows me to calculate a probability distribution over all of the events to take place. So I could apply that probability rule, and I could calculate, in this case, my probability distribution over all 4 of the variables, x1, x2, z1, and z2. I could calculate that big joint probability distribution, and then having done that, I could calculate the conditional distributions that that defines. So in particular, I could calculate the probability for z2 given z1. And once I do that, and I look at the numbers, I find out that I could have got to those same numbers in a different and rather more efficient way, which is I could have just used an expression that will be familiar from standard textbook quantum theory, right? This expression over here on the right-hand side of the equation, this is the expression that you would use if you were doing a basic problem in finite dimensional quantum theory and you were told that an agent prepares a quantum state in the Z1 state and then applies a unitary transformation to the state, and then the agent does a computational basis measurement and you are asked to calculate the probability for the outcome Z2. So we've got these expressions popping up that are familiar from textbook quantum theory. And it's significant because I'll just remind you, if you look at these axioms, there's no mention of the quantum state, right? There's no mention of a state vector or anything like that. There's also no mention of the idea of measurements, right? There is a probability rule, but it's not a probability for an agent doing a measurement. It's just probabilities for things happening. But nevertheless, when we apply this theory, we find that, at least within certain bubbles, reassuringly familiar expressions from standard finite dimensional quantum theory pop up. And so this is a special case of how, within a particular bubble, we can recover the statistics that we expect from standard quantum theory. Now, I'm not going to prove it to you, but I'm going to claim to you that all of this generalizes as much as you would want it to. So in particular, if you look at the paper on which this talk is based, I don't know if I mentioned it before, there's a paper on arXiv called Quantum Influences in Event Relativity. It's by me and John Barrett. If you look at that paper, then you'll find a sort of general recipe. And what the recipe does is, it starts with a kind of arbitrary experiment represented by some arbitrary circuit from standard finite dimensional quantum theory. And it tells you how to construct a sort of ontological circuit in our framework which will recover the statistics that you expect from standard quantum theory, at least within certain bubbles. And so in that sense, we are able to recover all of the statistics from standard finite dimensional quantum theory. We get all of the operational phenomena. But we also get more. So standard operational quantum theory kind of breaks down, it kind of becomes a bit vague and unclear when you start to consider nested measurements. So I'm assuming that most of you are familiar with the Wigner's friend scenario. In case you're not, I'll just give a very brief and probably not entirely adequate summary of it. What happens in the Wigner's friend scenario is there's an isolated lab, right? There's this lab with like thick concrete walls, so no information can get out of it. And inside the lab is your friend. And your friend prepares a quantum state, prepares a quantum system in a particular state, and then does a measurement on that quantum system. You are outside of this lab with the thick concrete walls. And And you, at the end of the experiment, after your friend has done the measurement, you can then sort of open up the lab, if you like, and you can do an arbitrary quantum measurement on all of the contents of the lab. And it sort of seems paradoxical by the lights of standard quantum theory, because when you apply standard quantum theory from the friend's perspective, you seem to get a quite different story compared to if you apply quantum theory from Wigner's perspective. And that's a bit of an issue, because standard quantum theory, it doesn't sort of unify those models in any kind of meta model, right? It doesn't give you an overall story of what's taking place. And it doesn't really give you a clear answer as to which of these two models is correct, or if they're somehow both right, how it is that you reconcile them. Now, our answer to that is that those two different models, roughly speaking, they correspond to different bubbles. So this is a circuit that represents the Wigner's friend scenario. And I'm not going to try to explain to you the ins and outs of how this circuit works. As you can see, it's a little bit complicated if you're not used to the interpretation. But I'll try to give you the basic idea. So you see, we've really got two copies of the same circuit over here. And on the left, I've opened up certain systems, and on the right, I've opened up others. So the left represents one bubble, and the right represents a different bubble. In the bubble on the left, the systems that are open up consist of the systems that you need to do the original state preparation at the very beginning of the experiment, and all of the systems that are relevant to the friend's measurement. Right? And in the second bubble, all of those systems that were present in the first bubble are still there. Right? Formally, the second bubble is a superset of the first bubble. But this second bubble also contains the systems that correspond to Wigner's measurement. And I'm not going to describe all the ins and outs, but I'll draw your attention to one salient feature. So one conspicuous thing you notice when comparing these two pictures is, on the left, you've got this event, I don't know if you can see because it's quite small, but this is an event labeled Z4. And on the right, the system is still in the bubble, but you don't see any Z4 there. And that's because over here, the preferred projective decomposition is the projectors onto the Z basis. Whereas here, because we've now included Wigner, that stops being the case, and now the preferred projective decomposition just contains the identity operator, so there's no non-trivial event here, which is why I've left this bit of the diagram blank. And so, what the bubble theory is telling you is that the friend only obtains any definite outcome in the bubbles in which Wigner is excluded. Right? So that's the analysis of the Wigner's friend scenario. Good. And that brings us pretty close to the end. Those are all of the examples that I wanted to give. So I'll just summarize and then maybe comment on one or two things before closing. So to summarize what we've seen today, the ingredients to this interpretation are independent of the interpretation itself. It's just commenting on some interesting structural aspects of standard quantum theory, in finite dimensions at least. The key point is that causal decoherence singles out projectors which admit probabilities. So more precisely, you know the story by now, relative to a bubble of n systems, we get two n projective decompositions singled out by causal decoherence. And then formally, mathematically speaking, this linear trace rule is a probability distribution. That enables us to posit an interpretation of finite dimensional quantum theory. That interpretation says that relative to each bubble, one history is realized. It's realized stochastically with a probability given by that probability expression. And we find when we apply this interpretation to examples that we can recover all of the phenomena from standard finite dimensional quantum theory, at least in the sense that we can always write down a circuit where within the right kind of bubbles we see the statistics that we expect. But we can also give precise models of the Wigner's friend scenario, which are, they're cases where the standard operational theory sort of can't really be applied with any rigor, at least not without extending the theory in some way. I'll just draw your attention to the fact that in the paper we do some more stuff. So our interpretation is closely related with the consistent histories formalism in a way that I'll elaborate on in a moment. But we show that certain sort of paradoxes that people have used to criticize standard consistent histories do not affect our interpretation in the same kind of problematic way. And we also use the central concept of interference influences in order to classify and in order to explain a kind of wide variety of different quantum phenomena. We're hoping that's going to pave the way for a big extension to the framework of quantum causal modeling, if you're familiar with that. Okay. And in the last few minutes, I just want to make a couple of other comments. So first of all...
You've got plenty of time, by the way. You've got about 10 minutes if you want it.
Okay. That's good. So I would be amiss if I didn't comment on the relation between the interpretation that I've laid out today and some other big three approaches. So some of you might be familiar with the consistent histories formalism. I'm not going to try to explain it to you in any detail if you're not. But roughly speaking, in consistent histories, projective decompositions are chosen by hand, right? You, the modeler, get to sort of freely choose the projective decompositions as long as they satisfy a consistency condition. And roughly speaking, that consistency condition is equivalent to the idea that the linear trace rule that I showed you on an earlier slide forms a valid probability distribution. Actually, not completely, because in consistent histories, you generally assume that you've got some initial quantum state, and it's equivalent in the case where you assume that that state is trivial. So you use the identity operator divided by the dimension. But anyway, the major point is that in consistent histories, you sort of choose the decompositions by hand so that you get valid probabilities. And therefore, consistency, or the validity of probabilities, it's not really derived, it's kind of imposed by fiat, right? It's a consequence of you making the right kind of choice. Whereas here, we don't choose our projective decomposition according to considerations of getting valid probabilities. We derive our projective decompositions from causal decoherence, and then it's a theorem that we get valid probabilities. And so one way you can understand our kind of formalism is as providing a kind of causal explanation of why the consistency condition could hold. And what about relational quantum mechanics? No doubt many of you will be familiar with relational quantum mechanics, and it's probably occurred to you throughout the last hour that much of what I've been speaking about seems to have something in common with it. And I agree. So here's a statement that you get in one of the papers on RQM, a relatively recent one by Andrea Di Biagio and Carlo Ravelli. So the statement is that events happen in interactions between any two systems and can be described as the actualization of the value of a variable of one system relative to the other. So, roughly speaking, the way that I read this is it's sort of pointing to the idea that events should be things that emerge out of interactions. And that's very much what we've been trying to sort of pin down formally in our framework. I wouldn't say, though, that what we have is exactly a formalization of what's stated here, because in particular, you see this statement, two systems, right? There's this emphasis on the bipartite case that you get in RQM, right? You're mainly talking about, I've got these two systems and they're interacting, and it emerges from the interactions between these two systems, these events. But what we've seen, particularly if you think back to our first example of the C-naught gate, you don't really get very interesting things happening when you only consider two systems. And you can't get interesting things happening by, I don't know, just combining many pairs. You sort of have to combine all of the systems into one big bubble in order to get anything interesting happening. So I think to some extent we're formalizing some ideas from RQM, but we're also learning that they have to be adapted a little bit. In particular, we're learning that there's this sort of holistic aspect of quantum theory that means in order to get the interesting events popping out, to get correlations between events, you really seem to need more than two systems. Now, I'd also like to make a more general comment about consistent histories and RQM. So it's possible that I might have slightly upset one or two people at the start by talking about moving beyond the big three in terms of precise realist interpretations without mentioning these two from the start. But there was a good reason why I used the word precise in precise and realist. Both of these interpretations, in one way or another, have been criticized for their vagueness, and I think justly so. So as I've said, I like this idea from RQM. I think it's a good idea, and to a limited extent, I think what I presented to you today kind of vindicates this idea. But the thing is, when you just leave it at this kind of sentence, when you just leave it in the English language, it's really not clear exactly what's being claimed. I think that physics proceeds by achieving conceptual clarity by the means of precise mathematical statements. And so Yeah, and I guess it ties to a broader point I want to make about going beyond the big three. So I think it's fair to say that it's kind of, we've got these sort of two communities of, we've got philosophy of physics on the one hand, and we've got foundations of physics on the other hand. Generally, roughly speaking, it seems to be the case that philosophers are more friendly to the big three approaches, whereas foundations people are more friendly to these kind of approaches, or particularly RQM. And I think part of the reason why a lot of philosophers are more friendly to the big three is because they don't like the lack of clarity, the lack of precision that you get from something like RQM, or in a slightly different way from something like consistent histories. And probably, understandably, a lot of people look at these specific examples and they think that for some reason, approaches that go beyond the big three are inevitably vague. Inevitably, they can't give you a precise and realistic description. But I really hope that today I've managed to convince you that regardless of whether or not you think the interpretation I presented is ultimately satisfactory, it is at least kind of precise in what it's claiming, right? It's using mathematical formalism in order to make its conceptual claims clear. They might be radical, they might be counterintuitive, but they're clear. So it is possible to go beyond the big three whilst maintaining the desiderata of precision, clarity, and realism. Good. And now, the final thing I want to do is I want to close with a sort of consilience argument, not necessarily for adopting the particular interpretation that I've laid out for you today, although of course I would love it if you did, but rather a consilience argument for the general idea of trying to move beyond the big three with a fundamentally causal approach to the interpretation of quantum theory. So here's a bunch of facts. Fact one, state-based interpretations are stagnant. They've been around for a long time, several decades, and generally speaking, universally speaking, they've not been able to command a consensus. That alone, I think, tells you something. It's not an encouraging sign. Fact number two, however, an event-based ontology naturally emerges from quantum causal influences. I hope to have sort of convinced you of that in the last hour. Fact number three, this is something I haven't talked about a lot, but it's something that's pretty well known. So at least for a broad class of general relativistic spacetimes, and possibly all of the general relativistic spacetimes that are actually physical, the metric up to a conformal factor supervenes on a causal partial order, right? A partial order that's often interpreted as having something to do with causation. Another way that this theorem is stated is as the partial order determines 9/10 of the metric, right? Really, most of the structure of spacetime is found in this partial order. So that's interesting. And it's particularly interesting, I think, when you combine it with fact 4, which is much less well known. So I've not talked about fact 4 today, and I'm not going to be able to explain it in great detail, but hopefully I can give you the gist of it right now. So there's a framework of quantum causal models that defines a notion of quantum influence between two systems, right? So not the interference influences between projective decompositions that I've been talking about. Causal influences between entire systems. And there's something that's really remarkable about these quantum causal relations. Quantum states are holistic, right? There's non-separability. If I know the state of A and I know the state of B, that doesn't mean I know the state of A tensor B. And so you might naively expect that causal relations are a bit like that too, but they're not. They're atomistic, they're separable. If I know the quantum causal relations between a bunch of subsystems, then I know immediately, I can deduce the causal relations between the composite systems. They're separable, they're atomistic. And I hope you can believe me when I say that one particular consequence of that causal atomicity is that quantum causal structures are naturally described by partial orders. When again, a priori, from quantum entanglement, you might suspect that they're not. So quantum causal structures are naturally described by the kind of causal structure from which 9/10 of the metric emerges. That's interesting. And for me personally, this isn't a deductive argument, this is a consilience argument, so I guess it's partly a matter of taste. But just speaking for myself, when I look at all of these 4 facts, I can't help but be pushed in a particular direction. It seems to me what all of this is telling us is that we should be aiming for a theory in which everything, in which ontology, spacetime, and the gravitational field all emerge from the same causal structure, namely the causal structure of a background-independent quantum theoretical model. This quantum theoretical model might look like the bubble interpretation I've laid out for you today. It might not. But in any case, I think that we should be moving beyond the big three with a new interpretation of quantum theory that maintains precision, maintains realism, and is based fundamentally on quantum causal structures. So that's me done. So I'll thank you for listening. I'll give a big thank you to my collaborator and the supervisor throughout my PhD, John Barrett. He's been really great, so big thank you to John. And also, I'd encourage you, if you're interested in any of these ideas, to check out the paper called Quantum Influences in Event Relativity on the archive for more stuff. Thank you.
Awesome.